Every time I ask a question in this video, you might want to pause it so you can have a think for yourself. Way better off if you think for yourself than just listen to me and what I think about these patterns and the questions that I'm going to ask about the different patterns that we've been looking at. And the first pattern I'm going to look at is just randomly off the top of my head, pick a linear pattern. And before we do this, you might want to have a look at a topic called limits. Now, you don't have to have a look at that topic because I'll give you just a general idea about it, but it could be worth your while looking at limits. I haven't gone through them, with my students before I do this, because this is actually helpful to get an idea of limits. So if I asked you to get any linear sequence, so something that looks like this, and to sum up that linear sequence forever. So if you got 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17, and you kept adding up forever and ever, what number would you get to? Or can you even contemplate that? Like, you need to think and like get out your calculator and start adding it up and see what happens as you start summing up your sequence. Where does your sequence, where does that head towards? Like the answer to that, like if you just kept adding up the pattern, like, maybe you got to 101 plus 103 plus 105 plus 107 plus 100 and so on, and you kept going and you eventually got to 517 plus 519 plus 521 plus 520, and you kept adding and adding and adding. Where would you end up, or where is that answer heading towards? And if you've had to think about it, you might see that you're heading towards infinity. Okay? It's not going to limit anywhere or stop anywhere or converge anywhere. It's just going to get bigger and bigger because you keep adding on massive numbers to it eventually. So you're going to head towards infinity. If we took another linear sequence, maybe minus 7, minus 5. I'm going to keep them similar or simple. No, let's go for 7, 5, 3, 1, minus 1, minus 3, minus 5, minus 7. And so on. If you started adding up this, so, you have this 5, that gives me 12, that gives me 15, that's 16. Now I'm starting to subtract though. And you keep going, so, minus 1, minus 3. Eventually get back to 0 here, but you have to keep subtracting because you have to keep going. So you'd be at 0 and you subtract 9, so you're at minus 9, and then you subtract another 11 and you're at minus 20, and then you subtract another 13 and you're at minus 33, and so on. Can you imagine what's going to happen if you keep doing that, if you keep summing up this particular sequence? Like, you'll eventually be subtracting 1001, 1000 minus 1003, minus another 1000, 1005. Can you imagine where your sequence is going to, the answer to that question is going to head towards? And if you have a think about it, you might realise that it's going to head towards minus infinity. And I would get you to think about the same with any quadratic. Do this with any quadratic that you can find. So the question that I had on a quadratic a few minutes ago was that quadratic. And if I asked you to sum up that quadratic sequence to infinity forever, like as in you just kept on adding the next number, where would you end up? And you'd hopefully realise again that you'd end up at infinity. So, depending on the sequence that's in front of you, a lot of these are what we call limiting or heading towards or converging at either infinity or minus infinity. Do that for a cubic as well. Pick any cubic that you want and sum up your sequence. And it's really good to start thinking about this and looking at this idea of summing up your sequence forever and see what happens. I'm going to look at a geometric. So if we have the geometric 2, 4, 8, 16, 32, and so on. If you summed that up, the 2 plus the 4, that's going to be 6, plus the 8, 6 is 14, plus the 16 is 30, then you're on 62, and you keep adding and adding and adding and adding. Eventually, where would you end up with the answer to that question if you kept summing up that sequence and kept adding on the next part of the pattern, just typing it into your calculator and kept pressing plus, you know, whatever. You would hopefully, I think, end up at an infinity again. Or, you know, we could obviously have the pattern going down where you're multiplying by a half, let's say. So if we looked at 32, 16, 8, 4, 2, 1, a half, a quarter, an eighth. Now this might be different, this one. Look at it, you get 32 plus a 16, you're on 48. Plus an 8, you're on 56. Plus a 4, you're on 60. Plus a 2, you're on 62. Plus a 1, 63. Plus a half, 63 and a half. Plus a quarter, 63 and 3/4. Plus an eighth. You wouldn't be on too much more than what we just said. Plus a 16th, again, only adding on a little bit more than what we just said. Plus 1 over 32. That's small enough again to be adding on. Eventually, if you think about it, you're going to add on smaller and smaller and smaller numbers. And eventually you're pretty much adding on nothing. If you think about it, if you were to sum up this sequence, eventually you'd be adding on like 1 over 64 and 1 over 132. Like they're tiny, tiny, tiny little bits to be adding on. So this sequence isn't going to converge at infinity or minus infinity like the other ones have. This one is an interesting one that we want to look at. It's a geometric where your common ratio is between minus 1 and 1. Or another way of saying that, it's actually written in your log tables, that the absolute value is less of the common ratio is less than 1. These are worth looking at. These are actually going to maybe be somewhat interesting in comparison to the other ones, because the other ones seem to just not converge anywhere. They don't seem to limit anywhere. These might, you know, we need to have a look at these and see, will they converge at a particular number? Like, will they not actually, because eventually you're adding on so little, will you eventually kind of just head towards a certain number and never actually even get there? You know, will this one actually ever get bigger than 66 maybe? Or it certainly doesn't seem like it's ever going to get bigger than 100, because you're adding on tiny, tiny, tiny fractions soon enough. So there is a formula in your log tables, and if you look to the SN formula of a geometric n over 2, nope, that's not it. Geometric SN is a times 1 minus r to the power of n all over 1 minus r. And we're going to get the sum to infinity. Like, we're going to sum up the sequence forever. Keep adding on the next part of the sequence. And when you think about that, if your common ratio is a fraction and you put a fraction to a very, very high power, throw that into your calculator, like put a half to the power of 10. Put a half to the power of 20. You get a tiny, tiny number, and that's only to the power of 20. Put it to the power of 100, and you will get a really, really small number. Like, that's it in scientific notation. That means move the decimal point 31 places in this direction. So let's put it to the power of 1,000. That's, okay, the answer to that is not, let's say 0, but I mean, it's such a small number that it's heading towards 0. So if you think about it, because my common ratio is a fraction, and if you put a fraction to an extremely high number, this will actually turn to 0. Or pretty much 0, it's so small. So you're going to end up with 1 minus 0 is 1 all over 1 minus r. It's a all over 1 minus r. If you go to your log tables, you will see that formula. And you can use that formula. Hopefully now you might have an idea of where it comes out of. You don't have to have an idea of where it comes out of exactly. We're going to look at that in another video. This is just giving you a quick idea of where it comes out of. So you can use this formula to sum up any geometric sequence that has a common ratio between minus 1 and 1. So let's look at the one we had. 32, 16, 8, 4, 1, 2, 1. And if we use that formula to sum up forever, A was 32 all over 1 minus a half. Throw that into your calculator. So we've 32 all over 1 minus a half, and you end up with 64. This sequence will never go above 64 if you keep adding it up. Like the 32 and the 16 we said give us 48, then we have 56, 60, 62, 63, 63 and a half, 63 and 3/4, and then 8. You know, it's never going to go past 63 or 64. This is looking at where our sequence converges. A lot of them converge at, well, they don't converge. They keep getting bigger and bigger and bigger and going towards infinity or minus infinity. The only interesting ones that seem to converge are geometrics, where the common ratio is between minus 1 and 1. Also can be said in this way. And when we want to sum up a geometric where the common ratio is between minus 1 and 1, and we want to sum it up to infinity, keep adding it up forever, we can use this formula, which is in your log tables. It's actually probably just good to point out that it actually gives you all the information here. So there's your formula, but it also says your common ratio has to be between minus 1 and 1. So we're going a little bit into more detail about geometrics. This isn't here for linear, because as I said, when we looked at linear, they don't seem to be anything interesting. They don't converge, whereas the geometric with a common ratio between 1 and minus 1 will converge somewhere, and we want to know where that is.